I must be unmuted now. Is that? Can you hear me? Well, you can hear me, but
Okay. Now they can
it should be fine.
Yeah.
Okay, so to people online who haven't listened everything that I said, I said we should be thankful to a lot of people in the exoplanet community and all of those who contributed to JWST and a lot of my collaborators here and all the funders. And thanks for having me here this morning. So we dive in, and what I'm going to talk about today is the Hycean paradigm in the search for life. I'll start with a big philosophical statement that for millennia, we as a species have been looking and asking for the big question of whether there is life elsewhere. So it's a common sense thing to wonder, right? Are we alone? Until recently, our notion, whenever you think of searching for life elsewhere, the common notion is a very common notion to have being on Earth is to look for Earth-like planets and life elsewhere as we know it on Earth. So that's just only normal. But if we want to find life on an Earth-like planet elsewhere, there are a few requirements, technical requirements that need to be met. First, we need to have a true Earth twin, obviously, right? So if you want to look for a Earth-like life on an Earth-like planet, we want to know if there is an Earth-like planet out there, a true Earth analog. And then we want to ask if we have the observational capability to find such life if it is indeed present on another planet. Right now, if you take a census in the field, to do a reality check, the answer is no to both those questions. Currently, we don't have an exact Earth twin that we know around a sun-like star. Okay? There are detection surveys that are happening in search of that, and that's a big area in itself. Lots of people are trying to find Earth twins. We also don't have the observational capability currently for a biosignature detection on an Earth twin. Even if we had an Earth-like planet around another star we know today, we don't have the capability to actually detect a biosignature in its atmosphere. Okay, so these are just some plain facts. So then if we want to search for biosignatures on other planets, what do we do? So the story has ended before it started, so to speak. So there are fortunately other avenues. So if we take the demographics of exoplanets over the last few decades, what we are finding, is there a pointer somewhere there?
You have to stick down.
Yeah, old-fashioned. The old-fashioned pointer, that's great. So if we take the demographics of exoplanet population, what we know is that the majority of planets are in what is known as the sub-Neptune regime, as we know it today. And these planets, what is the sub-Neptune regime? It's planets, I mean, different people define it differently, but the way I'm going to define it is all the planets between Earth and Neptune in size, smaller than Neptune, which is about 4 times Earth size, okay? So that planets in that range are unique because we have no analogs of those in the solar system. In the solar system, you have the terrestrial planets and then you have the ice giants and nothing in between. But in the exoplanet population, that is the intermediate range is where the planet population dominates, which is crazy to think about, but that's the reality. That's what we know. So there are a lot of them in number, but we also don't know much about them. Okay? So in terms of the current context, what we are going to ask is, well, we know Earth is inhabited. So we could ask which planets in this range are potentially habitable, right? Can there be other planets that are larger than Earth maybe and still be habitable? Which of them are conducive for atmospheric observations? And what are the possible biosignatures that may be detectable in their atmospheres? So this is an attempt to say that let's expand our scope a little bit than being fixated on Earth-like planets around sun-like stars and see if there are other avenues to detect the possibility of life elsewhere. So it's a very natural and traditional astronomers' way of going about things, right? Knowing that the universe is non-deliverably infinite. Let's just go out there and see what we can find. So it's a very common sense approach. And that's the approach I'm going to take today. So this is my outline. I'm going to introduce you to what we mean by exoplanet habitability, and then I'll introduce what the Hycean paradigm is and what are some biosignatures to look for and how detectable they would be. And I'll talk about a case study of K218b, and this is where we'll spend a significant amount of time in this talk. So getting from the theory to observational implications already with JWST, and that's where the big breakthroughs are happening. And I'll end with the future outlook of this topic. So to begin with, exoplanet habitability. So this is a very old figure, just a cartoon, and there have been various variations of it over the years, but it serves the big picture purpose here. So nominally, when people have been thinking about planetary habitability in the past, the common notion is if you put literally an Earth-like planet around a star of a certain size, how far from the star can the planet be and be able to host liquid water on the surface? Common sense definition, it's okay. And people have come up with what is known as the habitable zone, and that's basically that's the around any given star, that would be the region around the star where you can have an Earth analog planet with liquid water on the surface. You go too far, you freeze out all the greenhouse gases, and the planet is too cold. If you're close enough, it's too hot, it evaporates all the oceans and becomes uninhabitable very soon. So that's the optimal Goldilocks zone. And then if you go to larger stars and hence hotter stars, the habitable zone moves out, right? So you need to be farther to get the same level of irradiation. But if you go to smaller stars, you go closer. Your planet can be closer in and still be habitable. That's all. It's very simple. So then this is the basic notion that has been used for decades to look for habitable planets. Whenever you hear in the literature have a habitable planet, this is what people are talking about. Is it in the habitable zone? Obviously, you can also imagine that these boundaries depend on various factors, the specific atmospheric composition, the albedo or reflection, and so on and so forth. And there have been studies which have looked at the sensitivities for that, but we have some nominal definitions for what the habitable zone is. From an observational point of view, now you want to ask, well, we have a rough definition. How many planets do we have currently that fall in this zone that we can look for biomarkers, right? So when you ask that basic question, so I did this is a quick sanity check kind of plot. So I'm just showing you all the planets that we knew of until recently. This is not the latest, but like good enough. So showing planets in the radius period plane, radius equilibrium temperature plane, and so on. You see there are thousands of planets here, but then we want to look for habitable planets, right, in some search of biosignatures. So let's say if I take roughly an Earth-like temperature, order 300 Kelvin, and an Earth-size planet, how many planets are actually there? It's that little box, right? So you can literally count how many, like with the fingers on your hands, how many planets there are if you want to just focus on Earth-like planets. There are about like 4 planets, 4 to 5 planets max. Even with JWST, that's all there are, right? And even for those planets, you need hundreds of hours to be able to, with JWST, to be able to detect a biomarker like oxygen or ozone. Okay? So then what do? We simply don't have enough targets. And even the targets that we have are so faint that you need lots of JWST time. So now you can see why I started the talk the way I did. The motivation, my personal motivation, is to see if I can expand this box and still have the planets be habitable, right? So you see that even if I keep the temperature the same and just increase the radius, I start to get more and more planets. So if I increase the radius to, let's say, 2 Earth radii, then I have many more planets that I can look at. Okay. The question is whether such planets would be habitable, because we don't have a notion of such planets being habitable in the solar system. So if we take just the Earth-sized planets, then I said there are about 4 or 5 planets. There are 4 planets in what is known as the TRAPPIST-1 system. I'm sure people have heard about TRAPPIST-1, right? Somewhere. So this is a very late M dwarf. The size of the star is about 1/10 of the sun. So very late M dwarf. And there are 4 planets in the system that are in the habitable zone around that star. So lots of JWST programs are looking at those planets currently and have been over the past 2 years to see if we can detect any atmospheric signatures, and it is tough. Mainly because the signal to noise itself is low, but also because by the time you get to those late M dwarfs, they're very active as well. So they interfere with your observation. So it's a very challenging exercise. So in this talk, what we are going to say is, well, we know there are a small number of targets if we want to focus on Earth-sized planets, and we know that their atmospheric observations are challenging. We want to ask the big picture question: what are the limits of the planet mass, radius, temperature, basically the bulk properties, and the atmospheric conditions for exoplanet habitability? The idea is that if we could stretch those norms a little bit, we'll increase our catchment area, we'll increase our sample size, and then they may be more detectable. So we look at them with JWST and maybe detect potential biomarkers. Okay, so the rest of the talk, that is the motivation. So we have been doing this exercise for the last few years, 3 to 4 years, and that's where this new paradigm, the Hycean paradigm, was born.
Just one clarification. So you talk about the habitable zone, which is the separation from the main star. But now you talk about the size of the planet. What does it have to do with the?
Yeah. So that's a very good question. Habitable zone was defined for Earth-like planets. But let's say you put Jupiter in the habitable zone. That doesn't make it habitable, right? Because you have a much larger size, which means that you have the pressure increases as you go deeper in the atmosphere. If you have a thick atmosphere, the pressure and temperature conditions at the bottom of that atmosphere will be too high for habitability. Even if the equilibrium temperature of the planet is habitable, the planet itself won't be. You see what I mean? So we need to look at, in addition to how far the planet is, you need to look at the planetary bulk properties to see if they actually allow habitability. And that's what we're trying to do here. So that exact question is what we were faced with 4 years ago, actually. So it's very pertinent that you asked that question. So we were faced with this planet K218b. This was already in about 2019, 5 years ago. The planet has a mass of about 9 Earth masses, okay, 8.6 Earth masses, a size of 2.6 radius, Earth radii. But the equilibrium temperature is Earth-like, okay, 250 to 300 Kelvin, depending on the albedo. So we are confronted with exactly the same question that you just asked, is that the planet, if you put an Earth-like planet at that temperature or distance from the star, it would be habitable. But the point is, the planet was significantly bigger, both in mass and radius. And if you asked anyone in the field 5 years ago, would such a planet be habitable, including myself, the answer would be no. Because we had this concept that these planets would be called mini Neptunes, like miniature versions of Neptune, with thick hydrogen envelopes, which means the pressure and temperature conditions at the bottom of those envelopes would be too hot for habitability. So this would be written off immediately, and was as not being habitable. Except we tried to do a sanity check. We said, let's build internal structure models, see what the atmospheric composition is, and put it all together and see if the planet actually allows for habitable conditions. And that's what I'm going to tell you about now. As a brief primer before, you'll see a lot of atmospheric spectra in this talk. So I want you to know how it is done. So everyone's heard of the transit technique, right? I know we're all astronomers here, but just wanted to be doubly sure. So that's the transit technique. When the planet is going in front of the star, you see a dip in starlight. That transit depth is proportional to the ratio of the area, the projected area of the planet versus the star. Except when the planet has an atmosphere, you see that this radius has a wavelength dependent because the atmosphere absorbs at some wavelength more than others. So that's when you get a spectrum. And this is an example of that. For example, as a function of wavelength, this is just plotting a variation of the transit depth, and you see these various molecular features. These are showing a lot of observations in the pre-JWST era with Hubble Space Telescope. Okay, so you see some of these spectral features. All the points with error bars are the data. The solid lines are models in all of these cases. And we had measured water vapor in many giant planets with the Hubble Space Telescope, hot Jupiters. So those were all hot Jupiters. These were Neptunes, and going down to sub-Neptune, this is the only sub-Neptune that HST had measured, and the spectrum was pretty flat. But even down to Neptune-sized planets, we were seeing some spectral features back in the day with HST already. But what happened just before JWST was being launched in 2019 is that we were beginning to see some spectral features in sub-Neptune planets, even with HST. Okay? So this was one of those examples. This was with order 60 hours, 50 to 60 hours of HST time to obtain this one spectrum. So this is looking at 8 transits, but stacked together to get the signal to noise that's needed. And 2 groups had published this one spectrum. This is with the Hubble Wide Field Camera 3 between 1.1 to 1.6 micron. And you see this little bump. Okay, so that was a huge achievement for that time to be able to see an atmospheric feature of a small planet, 2.5 times Earth mass planet, Earth-sized planet, with the Hubble Space Telescope was a big achievement 5 years ago. And 2 groups had done it independently, so they saw those peaks. In those papers, at first, those peaks were attributed to water vapor, just as we have been doing for hot Jupiters, because we know water vapor has a strong feature here. But there was some debate on whether that was actually due to water vapor, because methane also has a feature at the same wavelength. Okay, so there was a degeneracy. Several studies have shown that there was a degeneracy between water vapor and methane, but there were also other claims that maybe it's due to interference from stellar activity, because it's an M dwarf. The host is an M dwarf, an early M dwarf, early to mid M dwarf, about half the size of the star, of the sun, which means that the star can also have water features. So if you have water vapor absorption in the star, it can also show up in your transmission spectrum as a planetary absorption feature. Okay, so there can be confusion. So some people have argued for that as well. So, we decided to take a look at the atmospheric spectrum and couple that with internal structure modeling and see what the planet would allow in terms of surface conditions. So this was our atmospheric retrieval of the same spectrum, and we also thought that that spectrum could be contributed by water vapor. These are posteriors of the composition: water vapor, methane, ammonia, and so on. So we saw that yes, there is a peak in the posterior of water vapor, so it could be water vapor. But we also saw that if you there is an upper limit for methane. This is a 2 sigma upper limit that is very high of methane. So it may or may not be due to methane, but it is possible. But we don't see much ammonia. Okay. Now, so that's just the atmospheric composition. So as crude as this observation is, and as degenerate as the interpretation is, there is one thing that comes out of all of this that is quite robust, which is that irrespective of what is actually causing the absorption, water vapor or methane, the background atmosphere is hydrogen rich. Because we talk about water vapor absorption, but still the amount of it is only 1%. So what is the remaining 90+%? It's hydrogen, molecular hydrogen. So what we have established from this observation already, that unless it is due to star spots or something, the feature, if it is due to the planet, then the atmosphere is hydrogen dominated. And as simple as that might sound, that's actually quite a big deal. The reason for that is that if you take just the bulk density of the planet, so that's the mass and radius I'm showing again, And these are what are known as the mass radius curves with uniform composition in the interior. So that's showing the radius, this is showing the mass on the x-axis. These curves, for example, the red curve is showing what the radius of a sphere of pure iron would be for a given mass. Okay, so you can, these internal structured models are straightforward in this sense, just if you want homogeneous compositions. And this is for silicate, that's for water, pure water. Okay, so you'll see that just the mass and radius of the planet is such that it lies slightly above the pure water curve, which means even if you have 100% sphere of water, you won't be able to explain the density of the planet. So what can you add? Any guesses? Hydrogen, right? So that's the most common compound that's lighter than water. So you can add a thick layer, a thin or thick layer of hydrogen, which obviously will be degenerate with all these compositions, but then you can explain the mass and radius. I'll give you one other like potential clue, which adds to the confusion, is that if you make the water hotter, for example, so this was for room temperature water, but in principle, if you make the water a lot hotter, that mass radius curve would come slightly higher up and still explain the density, right? So without making an atmospheric observation, you don't know whether there is a hydrogen layer or not. So the atmospheric observation told us that there is definitely a hydrogen layer, but we still don't know what the interior composition of the planet would be. So we did this exercise. We explored all the possible combination of the internal constituents and found 3 degenerate solutions. One possibility is that it is a mini Neptune. The classical notion of an ice giant is that you have a rocky core, you have an icy mantle, and then you have a hydrogen-rich envelope. It could be a miniature version of that. Okay, so this is iron, silicate, water, and hydrogen. Okay, so that's one explanation. Another extreme case is that you have not much water ice, but you have a rocky interior and a thick layer of hydrogen. That can also explain it. A third possibility is that it's a water world, which is you have a small rocky core, a lot of water in the interior, and a thin hydrogen envelope. That also explains the density. So as you can tell, it's a degenerate set of solutions, right? So there is no way to break it just yet. But in doing so, in just identifying this and using the atmospheric observation to establish a hydrogen layer, we have already made what was arguably one of the first instances in the field of atmosphere interior coupling to explain both the atmospheric data and the bulk parameters simultaneously. So what we did is we took the atmospheric observation and built an atmospheric structure model. You have the temperature structure of the atmosphere, and then at the boundary, at the bottom of that atmosphere, you use that as a boundary condition for your internal structure model, and then explore all the internal structure models that can give you consistent bulk parameters to what we are observing, right? So from a technical standpoint, please.
Is the surface below the hydrogen helium atmosphere or below the water layer?
So this is always at the atmosphere, in the hydrogen layer. Okay. So we did all of this exercise. So I'll zoom past a lot of technical details here, which you can ask me if you have more questions, because I want to get to the interesting JWST bit of the present. This is still, we are working in the past at this point 4 years ago. So if you do all that exercise with the coupled models, this is the loci of the temperatures. The red curves are the loci of the temperatures and pressures at the boundary between the hydrogen layer and the water layer. Okay, and what we find, and in the background is the water phase diagram. And what we find is that for most of the solutions, at the boundary, you have a supercritical water layer. The water would be too hot to be liquid. Okay, so that was as expected before. But for a small number of solutions, there is a chance that there could still be liquid water on the surface of the planet. And to us, that was the beginning of this whole exercise in establishing the range of parameters that can allow for planetary habitability. So the argument is that for K218b, while most of these solutions would be too hot for it to be habitable, there exists a non-negligible fraction of the solutions which allow for liquid water under a thin hydrogen-rich atmosphere. Okay. Of course, in order for that to happen, you need a lot of other things. You need a high enough albedo, you need the right internal temperature, you need the right atmospheric composition, and so on. But it is possible. And that's when we came up with the notion of Hycean worlds. Do people know what Hycean stands for? Some of you might. Hydrogen and ocean, as simple as that. A lot of times people ask me, I have never heard this Greek word. The minor problem is that it's not Greek. It's just a portmanteau. It's just a combination of hydrogen and ocean. Because these planets would be, for that particular solution, would be entirely covered in ocean. There won't be any land mass because you have so much water, a thick layer of water, that it's just ocean on the surface. And then you have a thin hydrogen-rich atmosphere on the top. That combination can allow for habitable conditions on the surface. And what we found is that there's a large range. We said, well, if K218b has this small set of solutions that are permitting habitability conditions, what is the full range in mass, radius, temperature, space that allow for such conditions? And we found that there's a wide range in radii, you can see, and masses. This whole sign region allows for such conditions, okay, for non-negligible habitable conditions. And there are a number of planets that we have identified that could allow for such conditions. So this is the Hycean mass radius plane. And you can already see that's K218b. So you could be up to 2.5 Earth radius if you have high enough mass and still be habitable. Okay. So that to us was the beginning of changing this notion of just focusing on Earth-like planet that we had before to now saying that maybe we can look at significantly larger planets that could be habitable, and let's just look at their atmospheres.
Just a question, but for each of these planets, in principle, the width of the space of the solution that allows your liquid water might be very different.
Yeah. Yeah.
But you're putting them together because you have some non-zero probability.
Exactly. As long as it's non-zero probability, we consider that, because that's all we can do at this point. We have to look at their atmospheres for further details. But to have a target sample, you want to be as generous as possible. Right? And actually, the smaller you go, the more habitable it becomes. Right? Because your atmosphere thickness, your conditions at the bottom become more favorable. So, and we did the same for the habitable zone as well. And we found, and people have done hydrogen-rich atmospheres for rocky planets before, and already knew that you could be very far from the star and still be habitable, because hydrogen is a very good greenhouse gas. But we did that exercise for these kinds of planets, and we found that that's the terrestrial habitable zone we looked at before. Now for these Hycean worlds, that is much, much more wider, because hydrogen is a very good greenhouse. So you can be a free-floating Hycean world and still be free-floating planet and still be habitable, which is crazy to think about, right? And then you could also be closer to the star for the right albedo and be habitable, especially for these tidally locked planets. The argument is that there is a chance that you could have the day side may be too hot, but the night side could still be habitable. So we call those as dark Hycean worlds, habitability with a permanent night side, right? And then just by doing that, you also increase the number of planets you can look at for habitability, right? So that's it. So that's the new paradigm that we are dealing with here, which has given us now a lot more targets. So in this paper already 3 years ago, we predicted that there will be nearly a dozen planets that we already know masses and radii for, that we can look at with JWST and detect potential biomarkers in their atmosphere.
My question, a dark Hycean planet with lots of water in the convection, would it be still okay?
Yeah, so it is not clear how much homogenization takes place. But if you have the right albedo and right day-night distribution, it is possible that the dark side is more habitable, and especially at the poles actually are always like significantly cooler than the equator. It's cool, right? So-
Another very short question. I'm a bit surprised, absolutely not from the people. So small planets can keep hydrogen in the atmosphere, even two Earth mass planets.
Two Earth mass, that's pushing it. That's at the edge. We don't know that just yet. The argument here is that if you have a hydrogen layer, you can make those habitable. Whether those have hydrogen layer or not is something you want to test with atmospheric observations. So that's it. So that's what we were arguing for this new class of planets, the Hycean worlds. And this would be the canonical picture, is that it would be an ocean world, typically warmer than what you would see on Earth. And those would be, the current candidates at least, would be mostly around M-DORs and will be hosting hydrogen-rich atmospheres. Okay, so that takes us, so we have established that there could be a lot of these planets, they could be habitable. The point is, what sort of biosignatures would we be looking for in their atmospheres? Now, on Earth, we know that oxygen, ozone, nitrous oxide, methane are prominent biomarkers. Would they be the same on Hycean worlds? The answer is most likely no, because these molecules would be unstable in a hydrogen-rich atmosphere. Okay, they'll react very quickly with the hydrogen to make, I mean, oxygen definitely, and without oxygen, you won't have much ozone. CH4, in principle, yes, but in a hydrogen-rich atmosphere, you can also get methane very easily, abiotically. So those themselves, the prominent biomarkers on Earth, the primary ones, are unlikely to be the biomarkers, robust biomarkers on a Hycean world. However, there are several secondary biomarkers on Earth, which organisms produce in very small quantities, but those molecules are produced uniquely by life. And there are examples, people have done this exercise on Earth before, and there are molecules like dimethyl sulfide, methyl chloride, mercaptan, and so on, that are produced by life on Earth. The problem is that they're produced in so small quantities, definitely less than part per million, often in part per billion, that if you look for them in an Earth-sized planet, it's hopeless. They won't be detectable. However, now you know that, now we know that Hycean planets can be significantly larger than Earth, and they have hydrogen-rich atmospheres, which means their scale heights would be significantly larger as well, which means they're more observable in terms of atmospheric spectroscopy. That gives you the clue that you can now target the secondary biomarkers so that even if they're present in small quantities, a part per million or few parts per million, they should be detectable in these Hycean worlds. Okay, and that is the exercise that we did. So I show you here various spectral contributions of these biomarkers people had already done for Earth-like planets, and you see that all these molecules, dimethyl sulfide, dimethyl disulfide, and all of these have significant features in the infrared. Okay, this is wavelength, and they have lots of infrared features, which means JWST should be able to look for these molecules in Hycean worlds, right? So I'll give you just some simulated examples. So this is just some early results from JWST on giant exoplanets. You may have seen in the press releases, like already from the very first observations. This is for a hot Jupiter. You see the spectacular data quality with JWST. Now we are going to push this to much smaller planets, habitable planets, right? So for hot Jupiters, it's clear that JWST is very good for giant planets to detect these spectral features. But if you come to small planets like TRAPPIST-1, these are simulated observations now. And what people have shown is that for across the board, for various TRAPPIST planets, you need tens of transits if you want to make an oxygen or ozone detection. Okay. This is just to drive home the point how difficult it is to measure biomarkers in even the TRAPPIST planets, which are our best bet for small rocky planets, around an M-DOR. You need hundreds of hours to detect a biomarker. But now let's see what we need with Hycean objects. So in that same paper in 2021, we did the simulated observations. These are all simulated observations, the points with error bars, and the solid curves are best fits for simulated retrievals. And these are all Hycean candidates. And what we showed that for these biomarkers that I just talked about, the DMS, methyl chloride, and so on, you only need order 3 or 4 transits to detect them robustly. And now suddenly we are saying that you need only a few tens of hours of JWST time to detect biomarkers if they're present in any of these objects, which is crazy, right? We're just in the first 2 years of JWST's operation, and we already have the chance to make these detections. Okay, so with that, let's dive into real JWST observations. Are you ready? Cool. So that was the build up over the last, I spent so much time on it because that's what we had spent a lot of time over the last 3 years, developing these theoretical intuitions and predictions for what can be done with JWST. So now let's see what we can do with JWST. So we go back to our favorite planet K218b, and before the first cycle, when the proposals were due for the first cycle of JWST, we said, let's put a proposal on this on K218b and do a reconnaissance study. Just say that we want to see what's in the atmosphere. We're not necessarily going to detect a biomarker, but let's just see what molecules are there and see even if we can detect some signatures of chemical disequilibrium, like molecules like carbon dioxide or methane or whatever it is there. Let's just see. Because as you know, with HST, we had detected an H2 rich atmosphere, but we weren't sure if it was water or methane. You remember that part of the story, right? So we wanted to make sure we confirm that first. So we asked for only 3 transits with JWST spread across the full wavelength range JWST allows between roughly 1 to 10 micron. And we would do it with 3 different instruments, NIRIS, NIRSPEC, and MIRI, on this target. So so far, we have 2 of those transits, NIRSPEC and NIRIS. NIRIS going from 0.9 to 2.8 micron and NIRSPEC from 2.7 to 5.2 micron. So I'll spare you a lot of details on the data reduction and so on, unless you're really interested, in which case just ask me, but I'll flash some pictures of what the spectra look like on the detector. So this is the NIRSPEC observation. The detector is split into 2. So you have a chip gap here, which will become important later. Okay. So that's the white light curve, which is a spectacular, as you can see, less order 100 parts per million at native resolution. That's the NIRSPEC. This is the nearest observation, which goes to close to red optical 0.9 micron. NIRIS, for those of you who are interested in observations, NIRIS is a slitless spectrograph, which means there are multiple orders and background sources. There are several background sources that come on your detector. So it's a lot of work to correct for all of those. And then there are 2 orders that can also have order overlaps. Suffice it to say that it is challenging to get a accurate spectrum out of these observations. But this is a solved problem. Okay, so we have done all of that. So I'll just cut to the chase and present you the spectrum. So this was the HST spectrum you saw. And with 14 hours of JWST time, with those 2 observations that I showed you, let's see what the spectrum looks like. Cool, isn't it? Just 14 hours of JWST time. And there are 5 methane features here. All of these peaks are due to methane. Okay. So you remember that degeneracy we had between water vapor and methane with the HST observation. Now it's robustly resolved. It's mostly due to methane. There could still be water. We have an upper limit for water, but there's a lot of methane, order 1%. All of these peaks are due to methane. We see another peak, strong peak, that's due to carbon dioxide, which we hadn't actually expected. Okay. But there we go. So we have carbon dioxide and so on. Now, to give you a bit more intuition, this is a plot showing the spectral contributions. So you can see, like, these are showing basically splitting the contributions from various molecules. So water vapor for that composition will be significantly less stronger compared to methane, and CO2. You see this big CO2 peak here and so on. But then you also see some other molecules that are also in the atmospheric retrieval in the model that could potentially be represented in the observation. So DMS, for example, is this huge peak. You remember DMS, the context in which I mentioned it, right? It's potential biomarker. We are not at a place where we can make any significant claims to that effect, but the point remains that it does have a strong feature within JWST's wavelength range. In this particular case, it is strongly degenerate with methane. So DMS has two features, both one is degenerate with methane, another degenerate with CO2, which means it's hard to tease out with just two observations, but it is there. So, so we do what is known as atmospheric retrieval. We again won't go into too much detail, but it's basically a Bayesian parameter estimation procedure. So you have your spectrum, you have an atmospheric model, and this model has all these molecules that I just showed you as free parameters, and then you put it in a Bayesian parameter estimation scheme, and you can get the posteriors of these various molecules. Now, when we do that exercise, these are the posteriors for the various molecules. Okay, so we detect methane very robustly, 4 to 5 sigma. We detect CO2 at 3 sigma, roughly. So these are both very confident detections. We don't detect water at any high confidence. We only have an upper limit. So with more precise observations, we might be able to detect some amount of water as well in the future, but we don't detect ammonia. We don't detect any other species, but we talked about DMS, and that's the posterior for DMS, right? I'll tell you why there are 3 posteriors in each case. But if you take the data at face value, right, just take the spectrum as is, we see a peak for DMS at 2.4 sigma. That's not zero. That's not that's not negligible. And the implications for that are very severe. If that turns out to be the case, they're very severe, because now we are saying that if we would be saying, if that is true, that there is some potential biomarker signal there. There is a possibility that some atmospheric process that we don't know so far is creating DMS. We don't know that yet. But currently, in all of atmospheric chemistry literature, both in the solar system and beyond, there is no single process that can make DMS and keep it stable in the atmosphere at those quantities, especially in a hydrogen-rich atmosphere. Okay, so there isn't a way as known so far. So if that detection remains robust, then or turns out to be robust, then we have a lot of work to do in the field to establish that can it be due to an abiotic source. Otherwise, that is showing some serious signs that we may be on to something here. Okay, but then most of our work in this paper went into trying to kill that signal. And that's why you're seeing 2 other posteriors. What we did is that, remember how for this NIRSPEC observation, I said there is a chip gap, there are 2 sub-detectors. This feature falls on both detectors, which means that if you put offsets between the 2 detectors, then you can play with the baseline of the feature, and then you can dilute the signal. Makes sense, right? So that is why, as you introduce more and more offsets between the 2 instruments, that is one offset. 2 offsets means offsets between the 2 instruments, but also offsets between 2 detectors of the same instrument, of the NIRSPEC detector. If the more offsets you introduce, the more dilute you make that signal, and you can make the significance go away to less than 1 signal. Okay. So maybe there is that offset, and maybe there is no DMS, and that's fine. But we have more observations coming that will test all of this. So we may or may not find DMS very soon, and this will happen within the next year. Okay, so those are some of the abundances that we are getting for the various molecules, and this is the summary that we are seeing now: a hydrogen-rich atmosphere with substantial quantities of methane and CO2. We are not seeing evidence for water vapor, methane, or carbon monoxide, and I'll mention briefly why that is important. But we are also seeing some marginal evidence for DMS, which is a potential biomarker, but marginal because of the reasons I just mentioned, and it may or may not be there. So we'll just have to wait for more data. And we're also seeing some evidence for clouds and hazes and low stratospheric temperatures, which are consistent with there being a condensed water phase, a liquid water phase on the surface. So now, I said we don't see ammonia, and that is important. Why is that? In a hydrogen-rich atmosphere, if you have a deep hydrogen-rich atmosphere like Neptune, for example, you expect to see significant hydrogen-bearing molecules like methane and ammonia and so on. And you see methane and ammonia in all giant planets. But if you have a surface under a shallow hydrogen-rich atmosphere, what that does is that cuts off the equilibrium recycling of these molecules from the lower atmosphere, and you start to deplete them. So previous studies, even before the observations were made, this were already in like 2021, have already predicted that if you don't see ammonia, but you see all the other molecules, that would be indicative of a surface. And the observations come out, and that's exactly what we see, right? So a deep atmosphere, you expect to see ammonia, and that is inconsistent with what we are observing. A shallow H2 rich atmosphere with a solid surface can also have the same effect. But as we know from our internal structure modeling, you can't have just rock and a thin hydrogen rich atmosphere because it won't match the density, right? So if you put all those arguments together, the best explanation we could come up with is that it has a shallow hydrogen rich atmosphere, which explains the lack of ammonia, but an ocean surface, which explains the bulk density. So it's a self-consistent story in that sense. So that's the summary. So the takeaway points for K218b is that the first detections of carbon-bearing molecules. So for all that I said, our focus is more on the habitability and potential life and so on and so forth. But in all of this, what you're missing is many steps of the story. In one observation of 14, like 2 observations of 14 hours, we have made a remarkable breakthrough in the field of even just measuring the first carbon-based molecules in the first place. If I came here in an alternate reality, if I came here and said, we detected methane in a small planet, regardless of whether it is habitable or not, that would already have been a big deal in the field. Because for more than a decade, we have been waiting on what is known as the missing methane problem. Methane had never been detected in a small planet before, exoplanet before, right? But in one observation, we have detected so many things that went to the back burner, so to speak. So we have detected methane, fine. We have also detected carbon dioxide, and we are even putting those together and saying there could be an ocean underneath. And now we have to work on our internal structure models to be able to explain the atmospheric composition. So you can see when I started this talk, I've said like there is phenomenal pace of development that's happening. That's what I mean. Where in 14 hours, you're making more advancement than we have made in the entire history of exoplanet atmospherics as an area. Okay? And then obviously all the other points I've already summarized. Regardless of the interpretation, to me, this is another major advancement because this is one of the few times, and the astrophysicists and cosmologists in the audience would appreciate this. There's a big tradition in astronomy and astrophysics of making a theoretical prediction before an observation is made. And oftentimes those don't hold. So this is a rare instance when you construct a theory, make a prediction, go make an observation, and the first observation says exactly what the theory had predicted. To me, that is an amazing feat. Now, obviously, we don't want to be complacent. We want to continue the pursuit and question our interpretation and come up with more theories. But the fact that that happened in the first place is a major success for astrophysics as a discipline. So that said, this does open a new era in exoplanet science both in our ability to characterize small planets regardless of the interpretation, but also now this launches. This provides a new launch pad in understanding habitability. Right now, we have a new laboratory in space to understand potential for habitability. There are various open questions on the interpretations. Is a liquid ocean surface actually possible? You need the right albedo. You need the right temperatures in the atmosphere and the surface and so on. So we want to know what is the albedo that is possible, both theoretically and observationally. So various studies are looking into it. What is the temperature structure? How is a deep H2 rich atmosphere possible with no ammonia? In other words, are there alternate mechanisms to get rid of the ammonia? And various studies are also looking into that. And what are the robust indicators for life on Hycean worlds, right? If for any reason this DMS signal survives, that is a scary prospect, because we are already saying that maybe we are looking at possible biotic mechanisms. But then we don't want to jump into conclusions, right? So we want to robustly test, are there alternate mechanisms to abiotically produce such molecules? What is the robust signature of this? And is life actually possible on Hycean worlds when you have just entirely ocean and no rocky surface? Is it conducive for life? And then more big picture observational aspects, we just looked at one object, K218b. Did we just get lucky, or is this actually a population we are talking about? So there are all these questions and all these interpretations, but suffice it to say, currently, the Hycean scenario still provides the best match to all the chemical constraints that we have so far. Okay, so in the remaining few minutes, I won't obviously be able to go into all these details, but I'll just touch up on a few to give you a sense of what's coming. What are the ocean conditions like on these planets? I get asked this question a lot. How do these planets actually look like, right? So there is a surface ocean, but how deep does the ocean go? Where is the seafloor, so to speak? Actually, if you do the internal structured calculations, which is amazing, what we find is that you actually can't have a rocky bed. The ocean is so thick that it quickly transitions from liquid into water ice. So you're looking at an ocean that just has more water in ice form as the seabed. Then you run into questions on, well, how do you get the bioessential elements? Because on Earth, you get the bioessential elements from the weathering processes, which has the rock involved. But if you don't have rock in the first place, how are you going to get those bioessentials? So there are all these questions. And then the ocean depths themselves could be hundreds of kilometers on several of these planets. So how does life emerge on these sorts of oceans and environments is a whole different topic. But this is just to give you a flavor of the kind of strange environments we are talking about. And we also did other studies looking at, well, is life actually possible? Are bioessential elements still going to be available? And what we found, surprisingly, is that you actually don't need a rocky bed to get the bioessential elements. You can get it through various other means, like normal asteroid impact with the same history as Earth can deliver enough material to the ocean for it to be enough for bioessential requirements. Same, you can also get precipitation from the atmosphere itself if you assume a solar composition atmosphere and so on. And if you do the chemistry over the evolutionary time frame, you also see that starting about a few hundred million years, you get all the prebiotic molecules that are needed to seed life in the first place. So anyway, so this is a lot of theoretical work. And then to the observational side of it, is K218b, did we just get lucky? Is it unique? Or are there more objects like that? And here I'm going to show you results from just about within the last month, actually. This is very fresh, where we made detections of very similar molecules, similar spectrum for a second candidate Hycean world. Some of you may have seen this result already, those in exoplanets and following the literature. But for the rest of you, this is the second planet called TY270d. It was in the list of the dozen planets I talked about, which we had predicted in 2021. You can see the similarity between the spectra. For a moment, we can all forget about the interpretation, right? Just think about as an astronomer, take a back seat, relax, think about it as an astronomer. And how often do you see two objects of a newly predicted class of planets show very similar spectrum? It's crazy. So this is what I mean by major advancements happening with JWST. This is literally the second planet that we had analyzed. And you see, it also has a methane peak. It also has a CO2 peak. right? But we are also seeing a third molecule. You see this peak here? That is the third molecule. That's carbon disulfide. Okay, that is carbon disulfide. You remember the biomarkers I was talking about earlier? I was talking about 5 biomarkers. One of them was DMS, another of them was carbon disulfide. Except this is a lot more significant than DMS. This we can't make it go away with moving offsets because all of this falls into the same sub-detector. So you can't kill it. But we have to be careful because CS2 is less robust than DMS as a biomarker. We can make, as it turns out, CS2 by just abiotic process. So we don't know. Okay. But the point remains, right? We predicted that you should be able to detect it. And we are detecting it. And this is the first time it has ever been detected in an exoplanet. So it's crazy. And then this is just overplotting the 2 spectra, and you can see how the features line up very nicely. And this is without any offset between the spectra. This is actually plotting the spectra on top of each other of 2 planets in 2 completely different systems, which is crazy. And then the only difference is this extra CS2 point in one of them. This planet is also hotter by 50 to 100 Kelvin than K218b. So we don't know if it is still habitable or not, but we are seeing these features. I'm showing this plot just to give you a flashback of what I was saying earlier. These were the theoretical predictions we made back in the day. And you saw that this is CS2. These are CS2 peaks we had predicted. These are CH4 and so on we had predicted. And now for 2 of these planets, K218 and 270, these are the observations. So you can again see this spirit of congruence between theoretical prediction and observations that's happening, right? So as much as I'm interested in habitability and the search for life and all that, fundamentally, like I'm an astrophysicist at heart, and when things like this happen, there is a meta level lesson to take. How you can make theoretical predictions based on fundamental physical principles, how you can make cutting edge observations to test those theories. Interpretations come and go, but the basic principles of the practice remain, okay? And that to me is rich. And I'll end with the future outlook. So I've introduced you to this new paradigm in the search for life. We will know in like 5 years or so from now, maybe there was never life on any on these planets. That's what maybe all the observations will tell us. But even if there is a low probability, there are a lot of targets. So our goal now is to just look at this vast diversity of planets that are available and search if there is any possibility. And we just have to get lucky once, right? So 3 fundamental advances I will mention from all of this is that we may already have made the first contact with potential habitability. We don't know yet, but the indications are there. And we will see there is more data coming. And as I've emphasized over and over again, what I'm most excited about is this congruence between theory and observation that's already happening at the cutting edge of exoplanet science for small planets. K218b was only 9 Earth masses, 2.5 Earth radii. QI270 is only 5 Earth masses and 2 Earth radii in size. So that's the smallest planet ever with a carbon-based molecular detection. So already we are seeing this happening for small planets. And then we are seeing a new class of temperate sub-Neptunes. 2 is enough for a new class, right? 2 is a class. The number will increase, but we have started. So we are already seeing a new class of temperate sub-Neptunes. Whether they're Hyceans, whether they're habitable or not is debatable, and we will establish that. But the journey has started. And we have several more planets that are coming. There are over a dozen planets with HST or JWST observations, but definitely more than 5 planets with JWST observations, good JWST observations. So over the next year already, you will hear more. There are at least 5 planets where we'll have similar data sets. So we'll see what we find. So finally, in the worst case scenario, we are making big breakthroughs on understanding a new class of objects, sub-Neptunes, that have no analogs in the solar system, right? Big astrophysics happening. In the best case scenario, we'll detect a biosymmetry. And the time frame of all of this is what is mind-boggling. We're talking about a couple of years. So where we started, we said, we have no facilities to look for life, and that's a 20, 30-year goal if we want to look for life on an Earth-like planet. Now we have enormously accelerated that process and saying there is a non-zero chance that all of that can happen in the next few years, 5 years. And that's what I mean by accelerated progress in the field. JWST is already operational, and towards the end of this decade, ELTs will come and add to the powerhouse that we are pursuing right now. So I leave you with this picture that we started with. Earth, that was our holy grail. But if we think of life as a universal process, then fundamentally, I don't think why we should restrict ourselves to thinking of only Earth-like planets. Right? From all physical parameters we know of, we know that they're extremely diverse. We know the planets are out there. So if life is also a universal process, a physical process, if you will, then why should it not also be as diverse? So I'll leave you with this last sentence. In my mind, knowing what I know, in my mind, the question is not whether we will find life. The bigger question in my mind is that, are we prepared to identify life as we do not know it, right? The possibility that we may already detect life well before we realize that that signature is actually due to life, right? So we are detecting the signatures first. And this is normal for astronomy. We detect astronomical phenomena a lot before we establish the theoretical underpinnings, the explanations behind it. So we may be on that same journey as far as the search for life is concerned. Thank you.
Okay, time for maybe a couple of questions. Thank you, Manu, for this talk. Because you mentioned at some point the coupling of the model between the atmosphere and the interior. Maybe it could be misleading because we attach, I guess, an atmospheric model to the interior. There's a lot of people that work on coupled models between interior and atmosphere and wonder about compositional coupling, the volatiles are present through the entire bulk of the planets between different components, and also interiors that are chemically active. And there are these alternative scenarios of models that are put out for K218b as well as TOI 2070b, which I'm also part of it, where the scenario to explain the data is very different, right? So
Yeah.
deep magma ocean.
Exactly.
So
yeah, so I do agree. This is what I was mentioning, is that there are a number of alternate hypotheses people are showing this, right? So there are all these hypotheses that are out there. For K218b, if you take all the data together, like the carbon monoxide non-detection, CO2, high CO2 amounts, non-detection of ammonia, the Hycean is still the best bet for that. Of course, for TOI 270, it's hotter, so there are other explanations. But this is what I meant, is that we will be arguing about the theoretical interpretation for a long time. But the data is there. To me, that's the important thing. And then for the coupling, so far what we have done is this, I mean, there are many ways you can couple, right? Is this disjoint coupling, in the sense that you solve the atmosphere based on your atmospheric observations separately. Use the bottom boundary of the atmosphere as the boundary conditions for your upper boundary conditions for your internal structure model. That's one way of doing it. Another way of doing it is to model it all together and do a joint retrieval of the internal and atmospheric structure to the data. That's a much more expensive process. You are probably trying to do that, and others will be trying to do that.
yeah.
But that is, that is the evolution of the field. We have to go at it in all directions, and that's where I will leave it.
So are you thinking about coupling like volatiles that are present in the ocean to see what their signature.
We do that. In our photochemical models, that is already being done. So you have fluxes coming from the ocean and how those interact with the CO2, for example. You won't be explained that CO2 unless there is an equilibration between the ocean and the atmosphere. And then the ammonia will be dissolving in the ocean. So all of that is being done, but it is still not 100% coupling as you would do in a full global model of the interior atmosphere. I don't think anyone has the capability to do that robustly right now. It's just more expensive, and it'll happen. We are all working on it, and we'll evolve as a field. But I don't claim, this is why I think I've been careful enough in this talk to say that we don't claim that we are absolutely seeing Hycean worlds, but we are getting there. And there is the data, that is the first step, and we have some models. And so far there is congruence, but there will be alternate hypotheses and a picture will emerge. That's the story of science, and this will be no different. So, yeah. So. Yeah, so helium, you can have helium, maybe at solar proportions or slightly higher, but the mean molecular weight is low. So the mean molecular weight we would get from just the atmospheric observation would be order like 2.5-ish, less than 3. So that already tells you that it can't be helium dominated. It has to be H2 dominated, but how much helium there is, we don't know.
There's a general question about how much the uncertainty in the radiative transfer model plays a role in, say, the DMS abundance that you refer from the spectrum.
So not necessarily the radiative transfer itself, that is, for transmission, it's actually quite straightforward, the radiative transfer itself, but the cross sections is probably what you meant. So we don't have proper line-by-line cross sections for DMS. We only have cross sections that are at Earth-like ambient temperatures. So the broadening could be different when you have hydrogen-rich atmospheres and so on, but we basically use what we have.
But you could, I mean, I guess if you assume you don't have clouds, or you have something
that won't make a difference because that's already in here.
It's already.
Yeah, so the models already include effects due to clouds and hazes, and we do get constraints on those as well. But that won't interfere with your actual like signal. What would make more difference is the cross sections.
They asked about the potential mismatch between the idea of having a massive surface ocean and then not seeing any water in that.
Yeah, that's a very interesting one, actually. For K218b, that is an expected result that even has been predicted before. And that's because if you do the same exercise for Earth, the answer will be the same. On the surface, you would have 1% of water vapor, right, in saturated phase. But if you go into the stratosphere and beyond, you get decrement by 2 to 3 orders of magnitude because of the cold trap. And that's actually what is keeping the water from escaping, right, is that water condenses out. And in transmission spectroscopy, you see the top layer of the atmosphere. So that is consistent with the picture what we are seeing there.
And would this be consistent over a range of temperatures, or does that mechanism break down?
So it would break down if you go to higher temp, like order 300 Kelvin or so. This is why in this second planet, 270, we do see water. So that's a good test of that, is that if you make it hotter, you start seeing water vapor. All the other features will continue to remain the same. So again, that is a good test of the theory.
I think I have to work with this on. But you can say for after I push it to go to the seminar. So let's thank Madhu again.
Thank you.
The ones who are coming for lunch, we will leave at 12:15 for them.